Right. So just a backtrack. That our revision was that any periodic signal in time could be expressed as a sum of sines and cosines in frequency. Periodic is the key for the Fourier series, and the particular form where you have it in the sum of sines and cosines is what we call the trigonometric form. And as we mentioned, the math people like this form. Oops. Right? The mathematicians like this particular form. But in our case, because of that thing that keeps coming up, there's a relationship between E sine, cosine, right, through Euler's formula. So we can express this in a slightly different form, which is the complex exponential form. Right? So instead of our sine and cosines, we have a sum of our E, J, K, omega naught, T, a sum of a series of things and some coefficients here. I think we normally just, I think we use C in our, what do you call it, in our notation. So some set of constants here, right? Oops, keep back in here, and we express the we like to, in our shorthand, we could summarize all the sines and cosines in terms of our e to the j k omega naught t. All right, whatever that form happens to be. Okay, but just our particular version of it, we prefer the complex exponential form, and then from there we move on. Right, so and then we did some examples and showed for certain types of signals. So like a single sine, if I give you a single sine, this has one frequency component. So that if this is time and you went to frequency and you plotted this, right? So instead of here you had time in seconds and amplitude, right? In here we have frequency in hertz. This has one frequency component in it. So if you go to the frequency side of things, this will have a single frequency component at some frequency f naught, whatever f naught is, right? So this is sine 2 pi f naught t. When you go to the frequency domain, all you have is a single line. I'm just putting the little arrow here, this little arrow, because I'm not too sure what the height is. Whatever this height is, of course, A is exactly this height here. Okay. So you have a single line in frequency, and if you have more than one component in here, as we said, sometimes you have these other signals that may be composed of multiple frequencies. So you have a funny signal here, but it's periodic. That's the important thing. You will have other components here, right? And because of the sinus, so because of the nature of the Fourier series. Okay, yeah, 1 second, guys. After give me a couple of minutes. Okay, back again. Sorry about that. As I say, it's going to be one of those mornings for a little while. Right, so where was I? At the point when if you have a signal now that is composed of multiple frequency components in time, again, the signal must be periodic, then you're going to get in the frequency domain multiple lines appearing. And the thing about the Fourier series is that these extra frequencies are always multiples of the fundamental, or what we call the base frequency or the fundamental frequency, right? So you will have components appearing at 2f0, 3f0, and so on. Some may be there, some may not be there, but they only occur at these integer points, which is the k here in our summation. All right, and of course, some of them, the amplitude may be what do you call it, negative. Huh? I'm just drawing all positive, but some may be negative, which means that it's out of phase with the original signal, the fundamental, and so on. So that's nothing too strange about it. All right. So that was a Fourier series bit, and lectures 15 and 16 sort of deal with that and the math behind it and so on. And of course, one that we paid attention to and has appeared already is this kind of periodic signal, the rectangular wave. So you have a periodic signal that looks like this. So it's going on in time, all right? And it has a particular width and a particular height. And the Fourier series, of course, we take the period sort of from here. So we could count the period. If the period is t, we normally say this is t over 2, and this is minus t over 2. The particular signal itself is running from t1 minus t1 to t1. And as you can imagine, if I were to ask you the sort of the components of this, the frequency components of this would change depending on how wide this is. And the frequency components we know are composed of a DC. We always said that there's a DC component, always a DC component, plus the harmonics. And this is something that we've met before. So like, for instance, the DC component is the average of what this is. So the average of this is somewhere in here. And if the signal, if the on time is large and the off time is small, then the average, DC average tends to go up. And if the on time is small and the off time is large, then the DC tends to go down. And we also mentioned this, that this was a form of something called pulse width modulation, which I think you have met in other courses elsewhere. All right, and we saw how to analyze that. And in fact, there are some questions appear almost every year on this kind of thing. And the ratio to the on time to the off time is, of course, what we call the duty cycle of the wave. So if the duty cycle is a 50% duty cycle, it means it's on half the time and off half the time. So the average value will be half whatever the amplitude of the signal is. And you could kind of so intuitively understand that, right? And then as you vary the on and off time, both the DC level and the harmonics vary. And in some cases, the harmonics, you may have only odd harmonics. In some cases, you have a mixture of odd and even, and so on. Yeah? Feel free, of course, to stop me at any time for clarification. So that was all well and good. And then we said, okay, what happens now if the signal is not periodic? And if it's not periodic, how do we approach that? And one way to do it, let me just clear some of the mess here. Right, if the signal is not periodic, so not, right, what next? Right, and the what next part was, like engineers, we kind of think outside the box a little bit. So what exactly you mean by not periodic? Not periodic means that it never repeats. Okay, so if I maybe could adjust my thinking to understand what that is. So if I have a signal that is like this, right? And then I take the signal, and so I have it here, no, and then stretch it out like this. And then eventually, so have the signal here again, and then put the next instant of the signal here. And in other words, I keep stretching the period t, getting bigger and bigger. So in my case now, what I say is that, okay, let's look and see what was happening inside of here. Non-periodic means it's not repeating, or that the period is so large that yes, it's periodic, but the period is just huge. And we took that approach, and what we saw is that we started with the Fourier series, and if we increase the period, as we're doing here, and let the period get bigger and bigger, and we make some adjustments, then the Fourier series now gets into a form that we now call the Fourier transform. All right. Let me see. I think I have the slides for that here. Fourier. Let me bring up that one first. Right, so let me share that. Right, and we covered it here. So that was the approach. We mentioned some mathematical conditions here, and it's just, as I mentioned, it's just that as engineers, you're going to have to remember that we're dealing with applied science, okay? And so one of the things with applied science is that sometimes the mathematics doesn't always work. It might look on paper that it could work, right? I mean, we are the people who decide that the root of a negative number, we give it a designation called minus j or minus I, right? Sorry, or I, j or I. But this in itself, try explaining that to someone who doesn't understand the rationale behind it, about the whole thing about a complex number. It you know, outside of mathematics, it makes absolutely no sense. So what we have to be aware of is that there are some conditions for things like the Laplace transform, for things like the Fourier transform, before I get into it, that have to exist before the mathematics actually works. You don't have to know them, but just be aware that they do exist. And if you're reading something, or you're doing some work, like later on, you might be doing some advanced work somewhere, you don't know where your career will take you, but always check back if you come up with something that the mathematics make sense, that it actually already looks, you could write it on a piece of paper, but does it work? Does it mathematically make some sort of sense? And that's what these conditions called the Dirichlet conditions are about. And that's as much as I'm going to say. There are certain types of things that you cannot find a Fourier or a Laplace transform for instance, signals looking like this, where the signal, it starts at low frequency. It starts at high frequency, so it's very high frequency. It gets to a low frequency and then stops, and then starts back at high frequency and then goes to low frequency and then stops. That kind of thing, where you have a discontinuity, right, makes it impossible to find a Laplace or a Fourier transform for it, okay? And then these kind of signals down here, where each step is half the value of the one before. You know that from you know, you saw some maths and logic that they would have done before, that if I were to move from point A to point B, and every step I take is half the size of the step before, I'm never going to reach the destination, right? So something like that is mathematically difficult to deal with, and you just need to be aware of it, okay? So the Fourier series, we let t go to infinity. And if I get to all of this, when we let the t go to infinity, then the Fourier transform, where we started off here, but this is the exponential form, and we substitute the results as t going to infinity and whatever, and we land up with now this version here, right? Which is a Fourier series for a signal whose period is infinite. In other words, a signal with no period, right? And we know already that a continuous that sums a sum over a period, over a set of numbers, as k gets to infinity, then this kind of summation, especially where the interval between the things get smaller and smaller, eventually become an integral. This is how we learn to integrate and to differentiate. You remember that? So in the limit, now, if this signal is continuous, sorry, if the signal is non-periodic, then we get a version, we are able to represent the signal in a version like this, right? And if we swap around, remember, this is what we want as the subject of the formula. We juggle it around and we get it into this version here, so that if I have a signal xt, the Fourier transform, now xt is non-periodic, that I could apply the quote-unquote Fourier series to it, and I get now the Fourier series version of it, which is an infinite sum now. So instead of a series of discrete sines and cosines, it's going to be a continuous expression in terms of E. And we call this now the Fourier transform of it. And of course, as I keep saying, if you're going from one domain, which is time to frequency, you must have a way of getting back. It's not a one-way. If it's a one-way, then any transform you have is useless. You can't just pick up yourself and go, and you never be able to come back. Okay? Guys, you're entering the Marvel universe at that point in time. Okay? So that now, you get the Fourier series for something that is not periodic, and we call it the Fourier transform. And this version, of course, now, the great thing about this particular version was that it looks like the Laplace transform. So if you remember the Laplace transform as the integral between naught, well, a little before naught and infinity of xt e to the minus st dt, if you could remember that, then if for some reason you forget what the Fourier transform looks like, then the Fourier transform looks just like this, except that s is equal to j omega, right? This shouldn't, this is questionable, right? Let me don't put s, let me take off that for a little bit. It's closer to the, where you can replace, that is better, s with, right? So it looks like the Laplace transform, and if you replace s with j omega, you get the Fourier transform. Later on, we will see when you put s equal to j omega, what happened, and we spoke about that when we did the Bode plot business, right? And and it leads from this actually, okay? Right, so everybody following you, you remember that bit, right? Yeah, no, maybe making sense? Yeah. Right, good. So, and of course, although I have a second screen here, sometimes it's not always easy to see the chart. So yell if something isn't making sense, so you can't remember. Right, so, and this, the particular section, sorry, the particular lecture went through the comparisons between the two. So where they were similar, right? This one is some notations from when we were discussing the December paper, right? The sort of properties. So the properties are very similar. If you know one good, then you should be able to know the other one fairly good. This one, of course, this property, right? You know your Laplace transform. If you have a derivative in the time domain, then the Laplace transform of that is for each power derivative you have an s in front of the transform of xt, and then you have these things called the initial conditions here. In the case of the Fourier transform, remember that doesn't apply because the Fourier transform integrates from minus infinity. The Laplace transform integrates from 0, well, a little before 0, right? And because of that, you have to take into account initial conditions. In other words, things that happen just at around the time when you're integrating. In the case of the Fourier transform, you're running from minus infinity to infinity. So there's no such thing as initial condition. They can't arise. You can't have something that is happening at the point where you're integrating, in other words. So that's difference number one. All right. And then we went through this, a unit step here. All right. The rectangular pulse. Okay. And this particular one, of course, led us to this thing with the sinc function, and we spent some time on that. All right. And then now, the other one that we were, just let me get that particular one now. The, right, so share that now. Go to, this one is slide 17. I am looking for slide, right, there we go, this one. Right, so after you did all of that, right, and some of the issues with bandwidth and the like, right, we'll talk about this in a second, and the properties here, right, then we come to this one, which is the question that led us here in the first place. What is the Fourier transform of a unit step? And what happened here is that we realize, okay, we have a signal here, but one of the things we have to remember with this is that the Fourier series, because you're dealing with frequency, there is a zero frequency component. And the 0 Hertz component is what we normally call the DC component, right? If you look at a signal like this, this is nothing, let's say this is volts we're talking about here, just for argument's sake, right? So 0 volts, and then it switches to 1 volt. If you subject any system to this, the system is going to see, well, over the period of time from before the system is turned on to after the system is turned on, is going to be subjected to nothing and then 1 volt. So from the frequency domain point of view, this is looking like you, on average, that you subjected it to a DC voltage of about half a volt on average. Okay, so that is where the main difference comes in. If you were to look at this and say the Laplace transform of this is 1 over s, and that the relationship between the Fourier transform and the Laplace transform is such that you seem to be able to get the Fourier transform if you replace s with j omega. So if the Laplace transform is 1 over s, the Fourier transform should be 1 over j omega. All right, but that is ignoring a part of the equation, which is this thing here, that we have a DC. So we have to consider what is the Fourier transform of this half a volt in the case of our unit step, because a half, right? Everybody following? You remember us discussing that as well in class, yeah? And if you do that, then, as you say, if you just simply try to find the Fourier transform of the unit step, you're going to get a piece of mathematics here that is not going to be able to be evaluated at all. As t goes to infinity, what is cosine and sine? They stay at cosine and sine forever. So we look at the average value, and then we try to find out what is the Fourier transform of a half. This is where we were. And what we did to evaluate that bit was to recall a little, another little property that we had developed before, that an impulse in time, excuse me a second. Okay, excuse me for 2 minutes again, please. Okay, I am back. And again, I apologize for that. I'll edit the video in a while. Okay, right. So what we were doing was trying to figure out a little bit here. What is the Fourier transform of a half? And we remembered what we do again. We try to reason out, and a lot of these things, you try to reason it out with based on what you know. Okay, so we know that an impulse in time gives us this constant value of 1 in frequency. So if you have an impulse in time, then the Fourier transform of an impulse in frequency, of course here, is this uniform signal that goes for all frequencies, right? Which is why we said this, again, this is another side why we said that impulse testing is so important in signals and in controls and in a number of other engineering applications, because when you subject something to an impulse in time, this is equivalent to subjecting it to a signal, an extremely wideband signal, theoretically a signal of infinite frequency components. We know that that's not possible, and we did some analyses where if you have, for instance, a signal of width, a very narrow and very high, and that's the other question that gives you this sort of sinc function behavior and so on. But back to what we're trying to solve is that, so an impulse in time gives me something, a constant in frequency. But what about a constant in time now? So in other words, if I have a constant in time here, so instead of an impulse in time, I have a constant in time. What does that give me in the frequency domain? And intuitively, we know, because of the dual nature of transforms, if you do something in time and it gives you a behavior in frequency, then if you swap the behaviors and you do something in frequency, it should give you the same sort of behavior in time. So in this case, an impulse in time gives us a constant in frequency. So a constant in time should give us an impulse in frequency, right? This is expected, right? So we need to prove it. So we figure that might happen, and how do we prove it? And this is where the Fourier transform, the properties of the Fourier transform come in. And what we do is that we go from the other way around and see, okay, I prove it by seeing if I have a delta omega in frequency, what is the inverse Fourier transform of that? And remember, the inverse Fourier transform is the same transform formula, except that the sign here is plus instead of minus, and we have this little constant, the 1 over 2 pi. All that is in the derivation in the earlier part of this lecture and the previous one, the slides. And if you go around there, you see that if you have a constant in time, and the constant happens to be 1 over 2 pi, you get an impulse in frequency. So in other words, this behavior here will happen if this thing in time was amplitude 1 over 2 pi. So 1 over 2 pi constant in time is going to give me a delta omega, right? Which is an impulse in frequency at the origin. So therefore, this is going to give me a delta omega. If I want to get a half now here, then the delta omega must be a little bit bigger. Right? So in other words, if I have pi delta omega now, then a Fourier transform of a half will give me an impulse whose weight is pi delta omega. So instead of this being a weight of 1, it now has a weight of pi, that's all, right? So therefore, the complete Fourier transform of the unit step is this, right? The part that we were able to derive from the Laplace, right, of our the Laplace transform, and this bit now, which we derive from our of the properties of the Fourier transform, right? And specifically the properties of impulses, which are right here, okay? Right? And then this particular lecture, of course, went on. It had that. What does the spectrum look like? Well, the spectrum is a very unusual spectrum. So you have an impulse, and you have, which is the DC part of it. So yes, you have a big DC component whose amplitude, if it's a 1 volt unit step, then you're going to have a DC impulse of about 3 volts. And then you have a spectrum that decays from, well, yeah, but the amplitude decays as the frequency goes up. Yeah. And then just to continue on that review, what about a Fourier transform of a periodic signal? And that one we did as a bit of a problem set. If you remember this here. So this is a single frequency signal. So therefore, if I give you this, you expect that the spectrum will have a single frequency component in it. All right, because of the fact that the Fourier transform runs from minus infinity to infinity, we normally have to cater for frequencies on the negative side. Remember, negative frequencies really don't exist, but because that we're dealing with complex, we using the J, the imaginary number, the imaginary designation, the complex exponential form, sorry, of the Fourier transform, and we're summing from infinity. Mathematically, we have to cater for negative frequencies. We understand in the real world that complex numbers, that the real and imaginary parts, the magnitude are really the sum of the squares of those two, and eventually the imaginary part comes out. But when you're plotting in the frequency domain, correctly, you have to consider that a single frequency signal like this will have not only an impulse at omega 0, but also one at minus omega 0. And the sinusoid, if instead I'd given you sine omega naught t, then, which was in this case would have been this sort of behavior here, who have drawn it a little bit scrappy, that now, right? So if yt was equal to sine omega naught t, then the spectrum here, again, you're going to have a signal at omega naught, but then you're going for the sinusoid, you're going to have the other impulse going the opposite way, a negative impulse. That just because sine and cosine are out of phase by 90 degrees. 90 degrees is a, in the complex domain, is 1j, right? Remember, j is our rotating phasor, which represents 90 degrees. So sine and cosine, because they're out of phase by 180 degrees, you're going to have this out of phase frequency for the sine. And it's all easy to prove using the properties, because you can't try it. If I put this into the expression for the Fourier transform here, right? Go back to the, where are we? Okay, I didn't have it written down here. If you were to, right, so right here, in fact. So if you were to go inside of here and you have xt here, if I were to substitute sine omega naught t or cosine omega naught t, you're not going to be able to evaluate that. Okay, it's going to run up because your limits are minus infinity to infinity, and there is no way to evaluate it at that point. So you have to go back to the properties of the transform and what you know. All right? So questions, that goes back to, believe it or not, this, where was the question? There we go. Right, so all of this was to help us answer this particular question. And in the doing this, we did looked over the Fourier series and the Fourier transform and so on. Yeah. So the answer here, right? You're asked to prove this. So you prove it by your answer to the question, therefore, and it's 6 marks. So the answer to the question would have been, okay, the unit step ut gives me 1 over s in the Laplace domain. The Fourier transform, we can get the Fourier transform for the Laplace transform in most cases by replacing s with j omega, right? So u j omega is equal to 1 over j omega plus the Fourier transform of the DC component of ut. And the Fourier transform of the DC component, you do that and you show that, or you could recall if you want, but the important thing here, you have had to show me this and tell me that the DC component of the unit step is a half. So therefore, this is plus the Fourier transform of a half. And then if you tell me from the properties of the Fourier transform that delta omega gives me, sorry, delta t gives me a Fourier transform of 1, so that delta omega, right, gives me a transform, an inverse transform of 1 over 2 pi. So the Fourier transform, therefore, 1 over 2 will give me a Fourier transform of pi delta omega, right? And you put it in there, and that's your 6 marks right there. Okay? But we went through the whole thing just to show the rationale behind it. So questions? Did a lot of talking, of course. Unfortunately, I interrupted us a little, a couple of times here. But you recall us discussing this. I'm hoping.
Excuse, sir.
Yes.
So based on what we're seeing here, is it that for the other Fourier transforms that the DC component does just go to 0?
Other transforms like what? Transforms
okay,
like what?
so like let me say we take well, any particular signal. If you take the Fourier transform, is it that the DC component in particular, does that go to 0? That is why we could make the assumption that you could say S is equal to j omega just by replacing it when you're taking the Fourier transform of another signal.
You have to watch the signal. So if I give you something looking like this, right? As soon as you see something like this, so it is positive 0, positive 0. This has a DC value, right? So you're going to have to take the sort of approach we took for this question. If I give you a signal looking like this, sinusoids and cosinusoids, notice that they go symmetrically about 0, so there's no DC component. So in that case, the substitution works directly. You have to watch the signal. If I were to give you something looking like this now, right? I'm trying to make this symmetrical, right? So if this is equally, if this is plus V and this is minus V, clearly the DC value here is 0. So then if you know the Laplace transform or something like this, then replacing S with j omega is going to give you the Fourier transform. All right?
Yes, thanks so much.
This case
make
now,
a lot of sense.
Yeah, you have to watch the signal. You must look at the signal first. If it has a DC component, then you could, when you replace S with j omega, there's something else that is going to have to be done. All right? Nice. So for argument's sake, I mean, I wouldn't do you this, right? But if I were to give you something looking like this, right? So this is, right? So this is a sinusoid, but it is a sinusoid that has a DC component on it.
Yeah.
That now, if you substitute your S equal j omega, you're going to get part of the answer. You're going to have to account for that DC value there. All right?
Okay.
Nice. So any other questions? As I said, we have, you have the slides, you have the recordings from the last time and our discussions now and the solutions, right? So it's up to you now in between, because the time is relatively short, but for you now to say what making sense and what not, and to let me know so that I can clarify it while we have the time together. Yeah? All right. And then, well, next time when we meet on Monday morning, we're going to look at this bit, which is the Z transform. So we'll do a little bit of a review of Z transform and Z transform behavior. All right. And then the other question here now deals with discontinuous signals and so on. So this is signal manipulation and the like. And then the last question now is a review of stability and the route through it. We did some of that for the December 2021 exam, but we'll spend a little more time going over everything here. All right, and the conditions, there are 3 sort of conditions you have to be aware of. All right, so this question is combining 2 things, simplifying a block diagram, a very simple block diagram, and applying the criterion, the route through its criterion to it to see what happens. All right. Okay, so any last questions before I close off here? We all right? All right.
Everything good so fast.
Right, I'm hoping so, right? And but you have to make, I mean, this is what these sessions are about. If things are not looking good, you have to let me know. That's the only way I'll be able to what do you call it? Correct it or clarify it for you. All right, so let me start.